Well, welcome to Math 104. Well, sort of. As per my email, the first hour is actually going to be a quick review of the first topic from Math 104, which is single variable integration. It seems to be that you probably are going to have trouble doing double and triple integrals if you cannot do single integrals. So that is the issue. I mean, in fact, double and triple integrals have to be reduced to single integrals, or multiple lots of single integrals. So you do have to know these integration techniques. All right. Okay, so here were the rough techniques, or a rough list of techniques of integration. So if you have an integral, and normally these will be definite integrals, so you're looking at a to b, but I'll probably just omit them because, of course, to find definite integrals, you need to find the indefinite integral in any case, so in most of the cases. So if you have a poly over a poly, if these are both polynomials, then probably you want partial fractions. Now, it would take me 2 hours to review partial fractions in general, but maybe I can do a very simple case. So the simple case I'm thinking of is when you have, well, there's, I guess, two simple cases. So a simple class of examples look like this. Linear function of a quadratic. So I propose to only look at that sort of partial fraction. And otherwise, you're going to just have to review your 104 or single variable notes. Or my book. Plug, plug, plug. There it is. It's only single variable. But it's in the library. So. Or you can buy it and then give it to your younger sibling or friend taking single variable calculus. Okay, so let's look at how to do this linear over quadratic case. Now, even that can be a bit of a pain. There's basically two cases. Case A is where you can factor the quadratic. Or quadratic can be factored. How do you tell whether you can factor a quadratic, by the way? What's the best way? You look at the discriminant, which is b squared minus 4ac, and if that is greater than or equal to 0, then it can be factored, because you've got to take the square root to find the roots. So if the quadratic can be factored, then what you want to do is try to express this linear over quadratic then. So that will look like something like ax plus b over x minus alpha, x minus beta, because I'm assuming you can factor it. And if there was a constant here, by the way, I'm going to just pull it out and absorb it up the top. So the idea is to write this as, say, c over x minus a alpha plus d over x minus beta. And you have to find these. Okay, so rather than go over the theory, I'll just show you an example of how you might find it. So suppose I take 2x plus 3 over x minus 1, x plus 4. Okay, so how would I bust this up? Well, write it as c over x minus 1 plus d over x plus 4. If this is going to be true, I should be able to multiply through by x minus 1, x minus 4, and have that be true. Okay, so this will give me 2x plus 3 equals c. The x minus 1 will cancel, and you'll just have x plus 4. Plus d, well, then the x plus 4 cancels, and you have x minus 1. So in this simple case, if you equate the coefficients of x, so equate coefficients of x, coefficients of x, and you will find here that 2 has to be c plus d, but if you equate the constant coefficients, you'll see that 3 has to be equal to 4c minus d. You see, all I did was take the cx plus dx. That has to match the 2x. So c plus d has to be 2. Whereas the 4c minus the d has to match the 3. So there are two equations to solve simultaneously. If you add them together, you get 5 equals 5c. So c equals 1. And then it's easy to see that d also equals 1. So that's the solution. So this means that if you have to integrate 2x plus 3 over x minus 1, x plus 4, now most of the time this would not have already been factored. I'm assuming that as step 1 you already factored it. In this case the coefficients are both 1, so the way to write this is 1 over x minus 1 plus 1 over x minus 4 dx, and there would be not much difference if there was some other numbers here. It's very simply, in this case, log absolute value x minus 1 plus log absolute value x plus 4 plus a constant. I'll call it c0, not to be confused with the c that I happen to use over there. But it's okay if you call it c. Everyone will understand that it's a different c. All right, any questions about that simple example? Okay, so again, I want to emphasize that probably the original question would have been 2x plus 3 over, and this will be x squared plus 3x minus 4 dx. Okay, so then you would have factored this. You would have noticed that the factors are minus 1 and 4. Now, this example is kind of a trick in a way. Can anyone think of a better way to do this particular problem? This very specific problem? Yeah. Yeah, notice that the denominator has derivative 2x plus 3, which is exactly on the numerator. So basic integration, here's a nice formula for here's a basic thing. You can just even write this down without a substitution. If you have a denominator whose derivative is in the numerator, you can immediately write this down as the log of the absolute value of the denominator. That's a really useful formula to know. So in words, function derivative of bottom dx equals log absolute value of the bottom plus c. I mean, it's more sophisticated as a formula, but you really are supposed to inspect this. So if I take this 2x plus 3 over x squared plus 3x minus 4, if you happen to notice that the top is the derivative of the bottom, you can just immediately write down the solution as the absolute log of the absolute value of the bottom. Is that the same answer as the one we got before? It is, because of the log laws. If you in fact factored this into your x minus 1, x plus 4, you will see you get exactly the same answer. Now, I want to emphasize that this only worked because of this 2x plus 3. It also would have worked if there was 4x plus 6 or any multiple of 2x plus 3. Okay, because then you could just take the multiple out. So for example, if you had 4x plus 6, you could have just pulled out a factor of 2. In fact, you should just pull out a factor of 2 to make it match, remembering that constants can go through the integral. Okay, etc. If you had any other function, instead of 2x plus 3, you had 2x plus 5, any non-multiple of 2x plus 3, so any other linear or just even a constant up there, then you would have had to use this method. But it's always good to check the other one first. All right, so that is how you deal with the case where you can factor the bottom. If you cannot factor the bottom, well, the most sort of common case is where you have, for example, x. Let's do this. Actually, let's do this. 5x plus 3. Okay, well, clearly you cannot factor x squared plus 9. So the way to do this is just to break it up into two integrals. The first integral, I'll pull out the 5, and you get x over x squared plus 9. And the second integral, I'll pull out the 3, and you get 1 over x squared plus 9. Okay, so these have to be handled completely differently. To do this one, notice that the derivative of x squared plus 9 is 2x. So actually, watch this. I want to put in a 2 here so that this matches. But I can't just do that. I have to put in a compensating 2. That's a nice little trick. You can use an extra line if you like, or you can do what I did and consolidate them onto the first line. So in order to do this, having done this, I can just write down the answer as 5 halves log x squared plus 9 for that term. And the reason being that the 2x is the derivative of the bottom. And as I've just said, you can just write the log of the bottom. Why did I not use absolute values? I could have, but why did I not need to? Yeah, x squared plus 9 is always positive. So it's not a mistake to put the absolute values. It's just more classy not to. I don't think that you should memorize too many integral formulas that aren't just the really basic ones like sine and cosine, etc. But you do need to know this. Well, you don't need to. You can get it from x squared plus 1, which is inverse tan. But it's really nice to remember this so you don't have to do the trouble of substituting. It's 1 over a inverse tan x over a plus a constant. So if you do this, and you recognize here that a happens to be 3, then you can just write down 1/3 inverse tan x over 3. And as it happens, this cancels out, and you have the simplified answer. Okay, so that's pretty much a canonical example if it's just x squared plus something. By the way, what if it's x squared minus 9? Does this work? No, what should you have done if this was x squared minus 9? Yeah, you're back in the other case. You factor it into x minus 3, x plus 3. So it's a very different scenario. This formula only works if there's a plus here. Only works if there's a plus here. All right. So if you have a linear term, so if this was instead x squared plus 2x plus 9, you would have to complete the square. And I guess it's possible that this will come up, but I don't know. This is not a... It would certainly be able to come up in 104. I guess it can come up in 201 as well. But really, the aim is to test whether you can do double integrals and triple integrals. You get a lot of the points just for reducing it to single integrals. You'll only get all the points if you actually do the single integral. But again, the philosophy is not to make sure that you can do all these techniques, although hopefully you can. So I don't know. It wouldn't hurt to review that, but I don't actually have time to do it. So let's just say if there's a linear term, complete the square, yada, yada, yada. So if you complete the square, I don't know, maybe I'll just set a damn thing up. What the hell? If you just had x squared plus 2x plus 9, if you check the discriminant, it's 4 minus 36. 4 minus 4ac, b squared minus 4ac. It's clearly negative, so you can't factor it. The way I would I'm not going to finish this. I'll just set it up for you. You complete the square, x squared plus 2x plus 9. You want to steal away a 1, because you know x squared plus 2x plus 1 is a square. So I'm going to write this as x plus 1 all squared plus 8. So you just want to just transform this like so. And then if you let instead t equal x plus 1, then you have x is t minus 1, dt is the same as dx. And so in t land, this integral becomes, x becomes t minus 1, so it's 5t minus 1. And on the bottom, you have t squared plus 8. And the dx is just dt. So this works out to be 5t minus 5 plus 3 is minus 2. over t squared plus 8. And the reason I don't propose to do this is because it's very similar to the above example. You just bust it up into the 2, as I showed you. See, we've got rid of the linear term. Admittedly, it's a bit more horrible because you have square roots of 8 instead of square roots of 9, but you can still do it, etc. So I'll leave it to you. At the end, don't forget to replace t by x plus 1 to get your final answer. It's wrong to leave it in terms of t unless you do it as a definite integral, but then you have to change the bounds as well. All right, so that's pretty much the story with partial fractions. Any questions about it? So that was method number 1. By the way, before I do method number 1, I should have done method number 0. As in, maybe I should have done this first. I apologize. You can shuffle your pages or cut and paste or mentally. It doesn't really matter. I kind of didn't even do some of the absolute basics, which were just the integrals that you have to know. So maybe I shouldn't jump the gun and should spend 5 minutes on these basic integrals. The most common is a power, which is very straightforward. You simply knock the power up by 1 and divide by the same thing, as long as the power isn't precisely minus 1. If the power is minus 1, you're dealing with 1 over x, whose integral is log the absolute value of x. Okay, this formula does not work if a is negative 1. Obviously, you're dividing by 0. So those are the sort of power rules. In terms of exponentials, you have to know this. I guess it's possible that you have a different base. So if you have a fixed base, a to the x, the integral turns out to be a to the x over the natural logarithm of a. But, man, you know, I really cannot imagine you being asked to do integral of 3 to the x. I guess it's possible. But there's certainly the e to the x one you need to know. And then your trig ones, this is a very common mistake. It's negative cosine x. Just emphasize the negative by breaking the chalk. Okay. Yeah, I cannot tell you how many times I've seen on graded papers integral of sine x is cosine x. That's a very nice way to throw a point or two away. However, the integral of cosine is sine. Look, just check by differentiating. The derivative of sine is cosine. Derivative of minus cosine is sine. Somehow everyone gets the derivatives right, but they just get the integrals wrong because it's the opposite. Okay, I'm going to do tan a little bit later and secant a little bit later, so that's not such a big deal. However, you should know that the integral of secant squared is tan, because the derivative of tan is secant squared, and that secant x tan x has integral secant x. These are just facts. I mean, if you differentiate tan, you get secant squared. You have to use the quotient rule. If you differentiate secant using the quotient rule or the chain rule, you find it comes out to be that. Both of these things have co-versions. Again, it's pretty unlikely that you'll find any co, but if you whack a co in front of everything so that you get cosecant squared x, this is going to be cotangent x, but because of the co, we have to put a minus. That's just the way it works. And this version happens to be cosecant x, cotangent x dx is cosecant x with a minus. Okay, then you have your inverse trigs that you have to know. I'll only give you 2. The most common, integral of 1 over root 1 minus x squared dx. That's arc sine x. You can write it as arc sine or inverse sine. Whereas 1 over 1 plus x squared with no square root is arc tan x. And this is a special case of the formula that I wrote up on the other board. I had an a squared here. So those are just your absolute basic integrals that you need to know. And you also should be able to adjust to having, well, I guess you could use the substitution method, but you ought to be able to do things like this. Integral of cosine 5x without doing a substitution. Without doing a substitution. See, it's just a multiple of x, so it's really a waste of time, in my opinion, to do a substitution for something so simple. What you want to do is write the integral of cosine is sine 5x. You just have to divide by 5. So if you've got a constant in there, if you ever replace all instances of x by a constant, you divide by that constant. Because when you differentiate this, the 5 comes out as a multiple, which would cancel out that 5. Okay? Similarly, if you had to integrate e to the x over 4. Well, x has been replaced by x over 4. I mean, you'd like the integral to be just e to the x, but of course it's x to the 4. You have to divide by a quarter, otherwise known as multiplying by 4. And again, reality check. Differentiate this, so you'll get a quarter that kills the 4. You just get what you want. You can always do a reality check by differentiating. All right, so that's sort of basic stuff. That's basic stuff. Here's another basic sort of thing. What's this integral? How do we do that? Yeah, just write this as x to the negative 3/2. And then the rule says you add 1 to that exponent. And then, so you get minus 1/2, and you divide by the same quantity. And so to tidy it up, you should write this as minus 1 over 2 root x, say. Or you could leave it as minus 1/2. Sorry, the 2 is on the top. Or you could leave it as minus 2x to the minus 1/2. That's fine too. So just be aware that these square roots, cube roots, etc. can often be done by converting to index notation. All right? So most of these formulas, if not all of them, can benefit from this constant rule here. You know, if I had secant 7x tan 7x, it would be secant 7x divided by 7. So a 7th out the front. Okay? Any questions about that basic stuff? Is integrating trig functions. Okay, so very common is some power of sine or some power of cosine. So suppose you have to integrate, actually you can kind of kill 2 birds with 1 stone. If you have some power of sine and or some power of cosine. This formula works if this is 0, this is like the 0th power, so it's only a power of sine. So this is like a 2-in-1 or a 3-in-1 formula. If you have this, the technique is to see the odd power, if there is one. So if one of these powers is odd, you're in very good shape. It's much, much easier than if they're both even. Okay, if they're both odd, then I guess pick the lowest one. So C's the lowest odd power out of the 2. Out of M and N. Okay, so what good does that do you? Well, what you want to do is pull out one of the powers. One power of this. And factor the rest, or convert the rest using sine squared x or cosine squared x plus sine squared x equals 1. That's just the summary in a nutshell. Of course, it doesn't really tell you anything unless you understand it in the context of an example. So here's an example. Suppose I had, say, sine to the 6th x cosine cubed x dx. Okay, so 6 is even, 3 is odd. I seize the odd power, and I steal one of it away, as per my instruction. So that will leave So I've stolen a cosine x away from the cosine cubed, and that leaves a cosine squared. And then, using the trig identity, I now say convert the rest of it by using cosine squared as 1 minus sine squared x. Okay? So what good does that do? Well, now the beauty of it is that cosine is the derivative of sine. If the sine and the cosine were reversed, you'd need to worry about a minus in there as well. But in this case, we now set up a substitution. T equals sine x. dt is cosine x dx. There's the cosine that we stole. That's why we stole it. And so this integral, carrying on from the previous board, is t to the 6th, 1 minus t squared dt. Notice that the cosine x dx is dt. And so you end up with a fairly simple integral after you expand this. T to the 6th minus t to the 8th. So that's t to the 7 over 7 minus t to the 9 over 9 plus a constant back to x land. And you get t is sine x. So you get the 7th power over 7 minus the 9th power plus a constant. All right, in the unlikely event that over here, imagine that instead of a 3, you had a 5. Well, then you'd have a 4 here instead. The only difference would be that you would think of cosine to the 4th x as cosine squared x all squared, i.e. you would have a square power there. But that doesn't make a difference. I mean, sure, you get a different answer. You'd have a square here. You'd have to expand this out, and you would then get 3 terms. But it's not very difficult. Okay, so that's why you can handle not just a cube power, but any odd power of cosine in that formula. Actually, it would even work if instead of a 6th power of sine, you could even have any power of sine. You could have an irrational power of sine, and this would still work. Sine to the pi x or something silly like that. So, pi power of sine x. As long as one of them is odd, this trick works very well. Any questions about that? All right, well, the next question should be, what if they're both even? If both are even, then you'll have, well, I'll just say use the double angle formula. So here they are. In this form, this is the most useful form. They come in a pair. Just memorize these. No. It's a good idea. See, they're nice when you memorize them in a pair as well. And as a reality check, cosine squared plus sine squared just gives you a half plus a half, because the other parts cancel out. Half plus a half is 1. So as an example, if you had to just do cosine squared x sine squared x, see, the temptation here is to use sine squared as 1 minus cosine squared or something like that, but it doesn't really help. It doesn't really help. It's actually going to waste time. So if you work this out, just use both of those formulas there, and you'll get 1 plus cosine 2x over 2, 1 minus cosine 2x over 2. Okay, well, that's a difference of squares. There's a factor of a quarter, so you have 1 minus cosine to the 4th, cosine squared of 2x dx. I can't fit the solution in there, so I'm going to have to move over here. Okay, so the integral of the 1 part should not fill you with any dread. The cosine squared part, well, actually, if it were me, here's an unnecessary step. I just simplify things a teensy little bit replace it by sine squared of 2x. But that's not really necessary because, once again, I have to bust out the double angle formula. Now, according to this formula on the board, sine squared of x would be 1 minus cosine of 2x. But you see, I don't have sine squared of x. I have sine squared of 2x. So this has to be 1 minus cosine of 4x. Again, we get another factor of 2. And now we can do this. We have an eighth. The integral, well, okay, 1 minus cosine 4x. No problem. Took out the factor of 2. Integral of 1 is x. The integral of cosine is sine. So I have a minus sine 4x, and I divide by 4. So you get 1/8 x minus 1/32 sine 4x, unless I made a mistake. Okay, so that's all I want to say about powers of sine and cosine. This is the sort of thing that I presume you knew how to do once, or I hope you did, but I can understand if you've forgotten it. The only reason I really remember it is because I've taught it like 50,000 times, and it somehow has stuck. I also wrote it in a book. That helped as well. But for you, I don't suggest that you try to teach it 50,000 times, nor write a book about it, but you could do some practice problems and remember the method. Okay, so I don't have that much time to go through all the other things, but I do think I should tell you how to integrate, say, tan squared. Anyone want to see tan cubed? Maybe. I don't know. I'm not going to go past 3. Tan is easy. Either learn it or know how to do it. The derivative of cosine is negative sine, so it's just minus the log of the denominator, absolute value. You can also write this as log of secant x. If you don't believe me, just add those two things up to see that they're the same thing, or rather subtract them from log secant x plus log cosine x is log of 1, because secant times cosine is 1, and log of 1 is 0. So this is actually the negative of this. All right. How do you deal with tan squared x? Well, the easiest way is to replace it by secant squared x minus 1. And that, I said, is just tan x. That's on the standard list. So if you had to do tan squared, that's not so bad. Tan cube's a little bit trickier, as are any high power tan. Get into all this reduction formulas stuff, but I'm not going to. I'll just show you tan, what the hey. So tan cubed, rather. So my proposal is to steal away a tan squared and use that exact identity to replace the tan by secant squared minus 1. So this is a very useful identity, by the way. I've kind of just thrown it out. I'm presuming you remember this identity here, which I just used before, but there it is. That's true for any x. You get it by taking cosine squared plus sine squared equals 1 and dividing by cosine squared. Nothing to that. Anyway, back over here, we split this into two integrals. Now this one we've already done. It's a lower power. It happens to be the first power. As for this one, you can do it with a t substitution. If t is tan x, dt is secant squared x dx. Beautiful. There's the secant squared x dx sitting there ready for us to use. So this is the integral of t dt. This one we've already done, and we've seen it's actually minus log of cosine x. As it turns out, the minuses cancel. I didn't bother putting a plus c yet because this already has a constant in it. So this will be t squared over 2. Now I can put in the plus c. I just have to make the t into tan x again, so it's a half tan squared x plus the log of cosine x plus c. So that's pretty unlikely, but maybe you need to know how to do powers. If you try it with, say, tan to the 4th or tan to the 5th, you'll see the method's very similar. As long as you just steal away one tan squared and change it to secant squared x minus 1, the same thing will work. You may have to repeat it a few times. If you start at tan to the 5th, then this one would be, for example, tan cubed instead, and you'd have a power of 4 there. Well, this one doesn't make a difference. You just have a different t there. Actually, you'd have a tan cubed rather. But here with the tan cubed, you know, you just repeat what we just did. So again, in 1 hour, I can only do so much. I would say for secant, it's almost too difficult to, or it'll take too long to tell you much about different powers, but it's worth knowing this. There's a nice little method for seeing this is true, but maybe I'll just add this to the collection. Just learn that. I don't know. If you have any space left in your brain, add that to the basic formula list. And of course, the integral of cosecant is minus the log of cosecant x plus cotangent x. You just co-eyes everything. If you don't believe it, differentiate this and you'll see it. It's quite nice, but it works. All right, so yes, what else? Well, there's this whole theory of trig substitutions. How does that work? Well, the typical time to use it is when you have the square root of a quadratic. If you have the square root of a quadratic, typically you use trig substitutions. An a counterexample, or you know, an exception, is if you had something like this. But there's a square root of a quadratic. You'd think you'd use a trig substitution, but the easiest thing is to use a regular substitution simply because the derivative of this bit is 2x, which is up there. Well, there's no 2, but the x is there. So t equals x squared minus 9 dt is 2x dx. Works. And I'll leave the rest to you. That's not a trig substitution. That's just a regular substitution. But if you had, say, an x squared or an x cubed or something else up there, this wouldn't work. This wouldn't work in general. There might be some special cases that happen to work. X cubed, you can get to work with that substitution, but x squared you can't really. So basically, if there's no regular substitution that appeals, square root of a quadratic, you've got to use a trig substitution. Now, if the quadratic has a linear term, you've got to complete the square. Again, that's going into a level of detail that I don't think is worth the time, because I just think it's very unlikely that it will occur. Not impossible. So I just want to concentrate on the standard cases. So there's 3 standard cases. So it depends whether you have the square root of something minus x squared, something plus x squared, or x squared minus something. Now, by the way, when I say the square root of a quadratic, this could also be the quadratic to the power 3 halves or 5 halves, etc. That's actually a square root in disguise. Any odd power of a square root is something to the 3 halves, 5 halves, 7, etc. This also, of course, applies. So there are 3 standard cases. There's 3 different substitutions that happen to work, and you kind of have to remember what they are. They all make sense if you understand the trig identities. So what I kind of want to do is set up a table. It's going to have 3 columns depending on which case you're in. What you need to be able to do is recognize which case you're in, remember the substitution, and generate. This is my working column that I'm going to give you. It's very generic. It's very generic, but it specializes very easily. So, check this out. If you're in the case with a squared minus x squared, the correct substitution is you have to start by writing x equals a sine theta. So So theta is the new variable, a is the constant. If this was, for example, 9 minus x squared inside the square root, a would be 3. So you start off with x equals 3 sine theta. You're going to need that dx just gets replaced by a cosine theta d theta. You're clearly going to need that. But in principle, that's all you need. However, it's useful to collect a couple of facts. So one fact is that a squared minus x squared is a squared minus a squared sine squared theta, which is a squared outside of 1 minus sine squared theta, which is a squared cosine squared theta. And the reason I think you should write that down is because you do have to take the square root of this, or some other power, 3/2 power. And this is really easy to take the square root of. It's just a cosine theta. Technically it should be plus or minus, but it always turns out to be plus. So again, a technicality I don't have time to deal with. Now, when you do your integral, you will get an answer in terms of theta, normally involving cosine theta or sine theta or tan theta or secant or some, trig function. And you need to go back to x at the end. A lot of the time. That's what you want to do. So in order to do that, it's very useful to draw this triangle here. All you have to do is realize that sine theta is x over a. Right? Because x is a sine theta. So sine theta is x over a. Sine is the opposite over the hypotenuse. And then by Pythagoras' theorem, this last side is root a squared minus x squared. And notice that that agrees with the case that we're in. And the beauty of this is, no matter what trig function you have, you can just read it off. So for example, what is tan theta? It's x over root a squared minus x squared. So to go back to x land, is very easy. Now normally I'd spend some time going over the other cases, but because I don't have a lot of time, I'm just going to write them down pretty much. If it's a squared plus x squared, the correct substitution is tan theta. You know that the derivative is tan here. The reason that this all works is because a squared plus x squared is a squared plus a squared tan squared theta. And the a squared factors, you get 1 plus tan squared, which is just secant squared. Again, very easy to take the square root of that. The triangle in this case, there's theta. Here we have tan theta is x over a. So if you draw an x and an a by Pythagoras' theorem, root a squared plus x squared. Okay, so there's the triangle in that case. And in the last case where you have square root of x squared minus a squared, here the correct substitution is a secant theta. Dx is a secant theta tan theta d theta. And again, x squared minus a squared works out to be, well, let's just do it. Secant squared theta minus 1 tan squared. So you have a squared tan squared theta. This is actually the only case where you need to be careful of the plus or minus, but a ridiculous technicality at this juncture. So no more words about it. Secant theta, this is supposed to be right angles. Secant theta is x over a. So that means that the hypotenuse over the adjacent is x over a. And then this is x squared minus a squared. Again, this matches the case we're in. So the point is, I don't really learn that. I mean, I just know what I'm looking for. Bless you. I know I need the x equals this, and that I have to learn. Then the dx, I know my derivatives. This stuff is just trig identities, and if you don't get something nice, you've picked the wrong substitution. And then the triangle just, again, it works by itself. So, let's just do an example. I don't know, suppose we do something like this. X squared root, let's do it simple. 4 minus x squared dx. Okay, so if I want to do that, I'm in the first case, so I'm going to let x equals 2 sine theta, and I have dx, and why the 2, by the way? Because it's the square root of 4. So my a is 4. A squared is 4. So a equals 2. So dx is 2 cosine theta d theta. And now I'm going to need 4 minus x squared is 4 minus 4 sine squared theta, which is 4 cosine squared theta. Nice. And I know I'm going to need my triangle eventually. I don't need it now, but sine theta is x over 2. So there's x, there's 2, there's 4 minus x squared. So actually what I've done is just duplicate the first column of the table on the right-hand side of the on the right-hand board, but just specialize to the case where a equals 2. Anyway, now I can start chopping and changing. X is 2 sine theta, so I'm going to get 2 sine theta all squared. Then I will have the square root. 4 minus x squared is already 4 cosine squared theta. So I just write that down under the square root. And don't forget the dx. The dx is 2 cosine theta d theta. Okay, so see how I assembled all these bits? I just used all my working here up to that point to get the answer that I want. And now 2 squared is 4. Root 4 is 2. And another 2. I think there's 16 there. I get sine squared theta, cosine theta. Again, maybe the square root should be negative, but it's not. Another cosine theta. And so I get 16 times the integral of sine squared theta, cosine squared theta, d theta. So I've reduced this other integral into a trig sort of integral. Now, here's a question. Do you recognize this integral? Yeah, we happen to have done it earlier. If we hadn't done it earlier, you would have had to just do it. But we did do it earlier. And I forget what the answer was. Could someone look back and tell me what this was? Here's one I prepared earlier. 1/8. I'm going to convert it to a theta minus plus a constant. Okay, so there's a bit of simplification. 2 theta minus a half sine 4 theta plus c. Now I said normally you can just read the answers off this triangle, but you can't really do that in either of these. In this particular case, theta, you just have to write as inverse sine x over 2. But you cannot read what sine 4 theta is, so you need to know your double angle formulas for sine as well. So actually here is the double angle formula for sine in the normal case. Sine 2 theta is 2 sine theta cosine theta. So that you're going to have to learn. Because in this case, we'll have 2 sine, not theta, but 2 theta. This is a pretty hard example, as it turns out. 2's cancel out, and we still need to use the double angle formulas again. Sine 2 theta is 2 sine theta cosine theta, and cosine 2 theta is 2 cosine squared theta minus 1. That one we've actually already looked at, but with cosine squared as the subject. Believe it or not, that's... So it's a bit of a mess. Let's see what we have. One term looks like 4 sine theta cosine cubed theta, and the other one is plus 2 sine theta cosine theta. Now we can use our triangle. Sine theta, well, that's just x over 2. But cosine theta is, in this triangle, root 4 minus x squared over 2. But we have to cube that. And then sine theta is x over 2 cosine theta, again, is root 4 minus x squared over 2 plus c. I'm almost exhausted. I'm almost done, luckily. 2 cubed is 8, 16. So this is a quarter x. And the classy way to write this is 4 minus x cubed, x squared to the power 3 halves. In this case, 2, 2, 2, I cancel out, and I just have a half x root 4 minus x squared. So unless I made a mistake, that's actually the answer in terms of x. Okay, again, I doubt that you get anything this complicated, but it's a good sort of example of a trig substitution. Any questions about it? You're all stunned. Are you stunned? Is this okay? Did you ever know how to do this? No. Okay, well. Well, hopefully you don't need to know how to do something that complicated, but you might as well protect your investment in your grade by learning a little bit if you have time. Especially, I would suggest, you've got this holiday period in December and January a little bit. That's a good time to go. Okay? I mean, here's the thing. This is math, no question about it. It's not as interesting as the math we're doing. It's very computational. I mean, it's nice that people have worked out techniques, but the fact is, everything I've done has been programmed into a computer. Everything I've done tonight, a computer can do in milliseconds. It's pretty sobering. So it would be nice if you could bring the computer into the final and not have to worry about it. But, you know, so I don't mean to say that this is just silly stuff. It's not silly stuff, but compared to what we're actually doing, this stuff is a little more trivial. So, all right, well, I don't have much more time for my integration summary, so basically I'm going to finish with integration by parts. That's the last of the techniques. Sorry? No? Question? Okay. This is the last of the techniques that I want to deal with. Substitution, of course, but we've decided to skip that. Integration by parts is especially useful when you have a product of two things. So basically, if you have something like x e to the x, nothing else really appeals. You certainly can't use partial fractions or trig substitutions. So what you have to do is pick part of this to be a dv and part of this to be a u. And what you want to do is, if you can, pick an exponential or a trig in general to be a dv, because they're really nice to integrate. So I'm going to call this a dv. I'm going to call this a u. So what's the good of that? Well, if u equals x and dv equals e to the x dx, then I need to know what du is, and I need to know what v is. So to get from u to du, you differentiate. Well, derivative of x is just dx. If this was x squared, it would be 2x dx. To get from dv back to v, you kind of just need to integrate this. And the integral of e to the x is just e to the x. You don't need the plus c for the integration by parts. So the beauty of this is that you have this formula that looks like this. The integral of u dv is uv minus the integral of v du. That's the general formula. So in this case, I'm going to write this is equal to uv minus the integral of v du. That's my working on top of u is x, v is e to the x as well. Integral of v du. Du is dx. So this is a very simple example. You get x e to the x minus the integral of e to the x, which is e to the x plus c. Here's a slightly more exotic example. Suppose instead I wanted the integral of x cosine 3x. Okay, again, I'll let this be u, and I'll let this be dv. So u is x again. This time dv is cosine 3x dx. Again, du is dx, no problem. But v is now the integral of cosine 3x, which is 1/3 sine 3x. Again, plus c not needed. So this is u v minus integral v du. Okay, what's u? X. What's v? 1/3 sine 3x. Minus the integral of v, 1/3 sine 3x. Du is dx. This is not so bad. This is 1/3 x sine 3x. Minus, well, integral of sine is minus cosine, so there'll actually be a plus there. And then you need to divide by the 3, and you'll get a 9th cosine 3x plus constant. Okay, one final example. To integrate just log x. You wouldn't think you need integration by parts because there's no product in there, but nevertheless, if you let the log be u and the dx be dv, the beautiful thing about letting, if you're ever going to integrate by parts involving a log, you always want it to be the u part. I'm not writing that down, but you might want to write that down yourself. If you have a log and you decide to integrate it by parts, most of the time you want the log to be the u part. And the reason is its derivative is quite nice. Watch this. U is log x, so du is 1 over x dx. So it gets rid of the log. Here, in this case, the dv happens to be dx, so v is just x. Now if you use the formula, you will have uv minus the integral v du. This is just working. U is log x, v is x, minus the integral v is x, and du is 1 over x dx. And in this case, the x and the 1 over x cancels, and you end up with just the integral of 1, which is x. So it's x log x minus x plus a constant. Okay, the same sort of trick works if you have arc sine or arc tan. So inverse trig here. Make a little note of that and practice it. See if you can do the integral of just arc sine x dx. You integrate by parts. Again, the derivative of arc sine is 1 over root 1 minus x squared, and you've gotten rid of the nasty arc sine. Question?
Isn't there something, I remember learning, like lipid or something? What does that stand for?
Lipid.
For picking U?
Right, so there's probably some rule with an acronym that I've heard of. It sounds like a fatty acid or something from chemistry. But basically, what's that? Log?
Logarithms.
Yes.
Then inverse trigs.
Inverse trigs.
Polynomials.
Polynomials.
Exponentials.
Exponentials.
Normal trigs.
Normal trig. Shouldn't it be lipte? I would have picked trig before exponentials to be the u. That's a bit weird. Okay, basically try logs and inverse trigs first as your u, then polynomials. So here, the trig I prefer as the dv and the u. So yeah, there's probably some rule there, but although, again, if you have to do e to the x sine x, I think it's better to let this be the u part. I think that's better. I don't think it works the other way around. But anyway, so that's why I would have said lipte. Anyway, maybe I'm wrong. All right, so look, that's just a sort of 1-hour crash course on basic integrals. I haven't done any definite integrals. Of course, any of these you can turn into a definite integral and just plug in the bounds. Okay, so I'm sort of taking that for granted. What can I say? I mean, again, it's not a course on single integration, but they do pop up, and it's silly to throw away easy points by not completing the problem because you don't know your single variable stuff. So any questions before I change course? Literally change courses and do Math 201 instead? All right. Back to multivariable land. Okay. I have it in mind to do a couple more questions on double integrals before I switch to triple integrals. Okay, and maybe you have some questions about double integrals. I did polar coordinates last week, which was actually a little bit unfortunate. It wasn't much of a review. It was more of a preview, but since I've already talked about it and it's on video, I'm not going to do it again. So did anyone actually want to ask any specific questions involving double integrals in either T or polar form? No one brought anything? You are welcome to bring your questions to these things, right? You don't have to. You're welcome to. You have a question, but it's about triple integrals. Okay, so let me just go through a couple more of these things that are actually from review session 7 worksheet. So one question has 3 parts. It came from a quiz in 2005, and it basically said sketch the region of integration and reverse the order of integration in 3 cases. So the first problem says the integral from minus pi over 2 to pi over 2, then the integral from 0 to cosine x of f dy dx. They're not really caring what f is. That's not what the issue is. F could be any function. They probably should have written f of x, y, dy, dx, but whatever. This is just something. It's more concerned about how to reverse the order of integration. So what this says is you do the y integral first, given a value of x. So what I'm going to do is realize that the x range goes from minus pi over 2 to pi over 2, and given a value of x, y is supposed to go from 0 up to cosine x. So that's the region of integration. So I'm just going to sketch y equals cosine x. I don't need all of it. I only need from minus pi over 2 to pi over 2. And I need y equals 0, which is this. So there's the order of integration. I mean, there's the region of integration. Okay, do you see how I read that off the thing? Now, how do you reverse it? What you have to do is work out for a typical y. So instead of an x, we're going to take a typical y and work out where it starts and where it finishes. So for a typical value of y, so that we're trying to do f dx dy here. Where does x go from? Well, if this is y, this x value is minus inverse cosine of y. And this is, well, this x value here is just inverse cosine of y. So you know what y is. How do you find out what x is? There's actually 2 values of x, and that's where you go from. So this is going to be from negative cosine inverse of y up to cosine inverse of y. And then you just have to work out what's the total range thing. Well, here's 0, and the intercept is 1. So you're going from 0 to 1. Okay? It's not trivial, and you certainly cannot tell just from looking at it. You have to draw the picture. Of course, the question says sketch the region and reverse it. But even if it didn't say sketch the region, I can't see how you can do it without sketching the region. Maybe you can have it in your head, but it's a little bit risky. You should draw the region. Okay, any questions about that particular example? Silence. All right, no questions. How about this one? Go from 0 to 1, and from minus x up to x squared. Well, let's draw it. The x range is from 0 to 1. The y goes between minus x and x squared. So we have to draw y equals x squared. It looks like this. And we have to draw y equals minus x. It looks like this. So the region, x only goes between 0 and 1, is that. Now, in order to reverse the region of integration, or the order of integration rather, you have to take a typical y and see where you go from. So start from left to right. The first thing you hit is x squared, and the next one you hit is x equals 1. So actually, from a y point of view, the x coordinate here is root y and 1. So you would think that the integral goes from root y up to 1 of f dx dy. The problem here is that's only true when the y is between 0 and 1. But so that actually just covers the upper half. The lower half is different. Here the x value is minus y, because y equals minus x, up to 1. So actually when you're between minus 1 and 0, you've got to go from minus y up to 1. And that has y range between minus 1 and 0. So there's no real way to get around this. From an x point of view, you're going between two curves, and that's one integral. From the y point of view, you're going between two curves, but one curve is just x equals 1. The other curve is x equals root y, but only between 0 and 1. Between minus 1 and 0, the curve is minus y at the bottom instead. Okay, any questions about that? Okay, go ahead, and I'll come back to you.
Up to 1 instead of 0 for the square root of y.
You mean over here?
Yeah, the upper bound. Yeah.
Okay, so when y is between 0 and 1, so this integral only cares about y between 0 and 1, which means 0 to 1. So I'm covering up the bottom half of the picture. Okay, so for a typical value of y, I have to see what is the first x when I enter the region, and what's the last x when I exit the region. So the entrance value is this x coordinate, which is root y, and the exit value is 1. In this part of the curve, the entrance value is minus y, and the exit value is 1. Okay, so this one is completely different from that one. Another question.
I have a little bit of trouble with the signs sometimes.
The sign, as in S-I-G-N.
Yes.
Okay, where is the ambiguity in the sign here?
In this case?
Yeah.
Well, I think, well, I'm not sure.
Okay, so let me tell you how you deal with the sign. Again, this is S-I-G-N, not sign, trig. Okay, so the way I'm dealing with it is I start at y, okay, and I move to the right. And the one I hit first, I put on the bottom. And the one I hit second, I put on the y. Now, of course, if the region looked like this, then I don't start at the axis. I sort of start well. So I'm going to start well over here until I hit it, okay? And then the other one, I just have to write in order.
Right,
Okay? So that's all there is to it.
Increasing direction.
Yep. Of course, if you're doing it in the x thing, you take the bottom to top. If you do that, you'll always have these things in the correct order. And again, here, I wouldn't write from 0 to minus 1, because that would be reversed. Okay? There may be a proper interpretation of it, but not in terms of a double area integral. The only way that would be correct is if the original integral had this sort of stuff reversed. But that's a silly trick to play, and I can't imagine that we'd do that. Okay? Well, it's possible. Okay. Any other questions about this example? Okay, one more. Double integral, minus 1 to 2, x squared minus 1 up to x plus 1. The bottom curve is x squared minus 1, which is a parabola that actually goes through here, has an intercept at minus 1, and goes through 2, 3. So you have to know what that looks like. The top curve is a line that actually goes through minus 1 and 1, and also hits 2, 3. Has slope 1. So this is y equals x plus 1. And that's the region. Okay, so that's all very well if you're going in terms of x, but if you're going in terms of y, again, you have two different paradigms. The easier one is through here. So suppose you pick a y. The first thing you hit is this curve, so you need to invert y equals x plus 1. Well, here, the x coordinate is y minus 1. That's easy. What about this x coordinate over here? Well, you need to invert x squared minus 1. So you do that by adding 1 and taking the square root, and I'll have x is root y plus 1. So in this part of the curve, anything above 0, once again, that's what you have. So there's going to be two integrals. The second one, you can write them in either order, of course, but the second one is that you go from y minus 1, that's the left point, up to the right point, which is root y plus 1. And that's true for the y values between 0 and 3. This will be the case for any of these lines here. You hit the line first and then the parabola. F dx dy. But we still have to deal with the y values between minus 1 and 0. So what do you hit first? You actually hit the left branch of the parabola. Then you hit you're in the region and you emerge at the right branch. Well, the right branch still has x coordinate here, root y plus 1. What is the x coordinate on the other side? Negative, right? When we inverted this, we said x squared equals y plus 1. We've got to take the plus or minus square root and realize that this branch over here is the plus, but this branch, which we need now, is the minus, root y plus 1. So this is going to be negative root y plus 1, which is what we hit first, up to root y plus 1. Okay? Any questions about that example? Excellent. How confident do you all feel about, say, being able to do those questions? I mean, obviously, you practice some more and study, but, like, is this good? Is this good? Do you like this? Question.
Another question. How come you couldn't do that one right there? Couldn't you just do that with a single integral?
You mean a single double integral?
No.
A solitary double integral?
I mean, can't you just... I don't know, it seemed like you could just subtract, you know, do one, a solitary, yeah, single integral, one variable, just subtract the two functions, and then that's it.
Okay. If you just had the integral of something dy dx, without the f, it's just the area of that region.
Right.
And you could solve that integral by taking the integral of the difference. But that's just the area weighted by, say, the function. That would be the case if the function was 1 everywhere.
Right.
But if it's not, then you kind of have a different height here and a different height there and a different height there. So you can't do it as a single integral. You need to do it in a double integral. Right. But now, the fact is that sometimes the double integral can only be done in one direction. We saw some examples of that. Sometimes it's impossible to do it one way. So you have to reverse the order of the integration. So this is a technical question that it just says, show that you know how to reverse the orders of integration. Okay? We haven't done any of the integrals because we don't know what f is. But at least we know that we have the tool to reverse it if we need to. Okay? Which, as I said, sometimes you do. All right. I better do a polar coordinates question, just one more to revive our knowledge of it, and then I'll do triple integrals. So this is similar to one we did last week, but I thought I'd do another one because it's kind of cool. The region that we want to integrate is this. So that's called R. And we want to find the integral of x squared plus y squared dA. Double integral. Okay, and it even tells you use polar coordinates. So let's draw the region. This is a circle, center 0, 1, of radius 1, or the interior and boundary of such an object. All right. So I told you in polar coordinates, you have to work out what the theta range is, and you have to work out what the r range is. So if you take any ray like this, you're clearly in the circle already at r equals 0. So r is going to go from 0 up to somewhere. To work out what the somewhere is, we actually need to work out this distance. This is what we need to work out. Well, here's theta. That's always true. Theta is the angle made to the axis. So here is a very similar trick to one we did last week. What I do is I draw in this and realize that the angle in the semicircle is a right angle. So this is 90 degrees minus theta here, so this is another copy of theta. Bit of geometry there. That's pi over 2 minus theta in there. So what does that mean? It means this distance here is 2. So the distance equals, let's call it d. So sine theta is d over 2. No, I'm sorry. Sine theta is d over 2. So d equals 2 sine theta. So the upshot of this is that the low value of 0, the low value of r is 0 in the circle, in the circle, in the circle. When you reach exactly 2 sine theta, where this is theta, you emerge from the circle. Clever. Not easy. Helps if you've seen it before. By the way, this also works in the second quadrant because sine theta is positive. So, when we integrate, the r value is going to go from 0 up to 2 sine theta. Something. What about theta? What is the first value of theta that we find that we are actually in the circle? How low could theta be? If it's 0, we're not quite in the circle, but that's okay. As soon as we get any positive angle, we will be in the circle. So we've got to start at 0, work our way up, 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 and stop at pi. So the theta is going from 0 to pi. Now, here's the thing. I told you last week that for polar coordinates, the dA is not dx dy. It's not just dr d theta. It's r dr d theta. You need an extra r. It has to be there. Now, what about x squared plus y squared? We need to convert that. You could use x is r cosine theta, y equals r sine theta. We know x squared plus y squared is r squared. So there's our double integral. So now we just have to do it. You get 0 to pi, 0 to 2 sine theta of r cubed dr d theta. So we'll do the r cubed. You get 1/4 r to the 4th evaluated between 0 and 2 sine theta. And if you work this out, pull out the quarter, and you get 2 to the 4th sine to the 4th theta d theta. Aha! Now you see why I did all this trig stuff earlier. You're going to have to use your double angle formulas to do this. It's actually very similar to the one we already did. It had sine squared, cosine squared. It's very similar. I don't have time to do it, but I'll show you how to start. You write it as, well, you write it as sine squared theta all squared. The reason you want to do that is because we have a double angle formula, sine squared theta equals 1 minus cosine 2 theta over 2. Wasn't that funny? Okay, so then you expand this out. The 4's will cancel. You'll have 1 minus 2 cosine 2 theta plus cosine squared 2 theta. And to do the cosine squared, you have to repeat it and get a 4 theta. Okay? I'm going to leave it to you, because you need to practice these things. All right? Anyone who wants to know if you're right, email me, and I will gladly tell you. No? But I will if you email me. All right, no questions. Triple integrals. Have you already done something on triple integrals in class? Just
Yeah.
who has not done any triple integral? Okay, but that's pretty much where you're up to, right? 15.4.
Yeah.
Okay, good. Well, the good news about triple integrals is it's very similar to double integrals. Okay, you just got to iterate, but you've got one extra variable. So the basic idea, again, is that you have some function of 3 variables, and you have some region in space, not just in the plane, but some region. Could be the interior of a soccer ball, deflated, otherwise a cube, whatever it is. Some polyhedron, but it's a solid. At every point inside this solid is a value of the function. What you want to do is add up all those values. Of course, there's infinitely many of them, so what you really need to do is chop it up into little pieces, little cubes or rectangular prisms or something like that, where the function doesn't change very much, hopefully, on each one of them, and then add them all up times the volume of those little pieces in a Riemann sum type of way, and then take a limit. The reason, this is very hard to graph now, because what you want to do is take a w-axis, which is perpendicular to the x, y, z axes where this thing is set up. So you want a w which is perpendicular, which you can't visualize because you can't think in 4 dimensions. I use the u in the probable sense. I can't do it. I don't know anyone who can do it. Depends what sort of mood you're in, I guess, but I don't think anyone has really ever been able to think. Probably not. So whatever the case, there would have to be a w, and then there would be some variable height w superimposed above this, and you'd be finding a 4-dimensional volume of that hyper object. Okay, so forget it. You can't think of it that way. Instead, think of it as a different temperature at every point. You add up all these temperatures multiplied by the little regions that they're in and essentially average them. So this is useful for finding averages in particular of temperatures in different regions. The only way to do it is to add them all up and divide by the volume of the thing. So we're going to see the formulas for averages and volumes very soon. I just wanted to give you a sense of what this thing means. Again, maybe it makes more sense to just use so here R is a solid region. Maybe it makes more sense to use one integral there, but convention is a triple integral. We saw in double integrals that you have a Fabini's theorem, which allows you to express this rather mysterious looking thing as an iterated sequence of 2 integrals. Well, here you have 3. So you have to pick an order of dx, dy, and y, z, and we have 2 possible orders for double integrals, dx, dy, or dy, dx. For triple integrals, we have 6 possible orders. dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, dz, dx, dy, dz, dy, dx. Thank you. Thank you. So there's 6 different possibilities, and you can pick any of them. In fact, you may have to change one into the other. There goes my microphone. I better do another sound check. Still work? Good. All right. So, there's a lot of restlessness. Okay. So in order to see how to do this, suppose that you have decided that you want to use the order dz, dy, dx. Okay, in that case, what would you do? Well, you have some region that you want to integrate over. The first thing to do is to say, well, you're doing the z first. So what you want to do is project this down into the xy plane. So this is the shadow cast by that object. Now, of course, the object could be going through the xy plane, so it's not a strict shadow in that case. But, okay. So, having found that, what you want to do is pick an arbitrary point x, y within the shadow. and draw a line upwards perpendicular to that plane, i.e. parallel to the z-axis. And you need to find out where z first enters and then where it leaves. Z in, z out. And this will depend function of x and y. So this involves both x's and y's. Again, function of x and y. So you're going to set up your integral f of dz, dy, dx. You need z in up to z out. But again, I want to emphasize that this involves x's and y's, maybe. Well, x's and y's involves x and y. Perhaps not both of them, but it could. Involves x and y. Okay, so having found that, what you now need to do is do the integral over y next, because that's what we've chosen. So what this means is you now have to fix an x. So through this point, you now draw parallel to the y-axis. And you're going to now have a y in and a y out. So going again in the positive direction. And that depends on x. This is a function of x. And this is a function of y. Sorry, this is also a function of x. Okay, so the point being that you do not draw this line through your arbitrary point in space. You do it through the base region. And then this thing works. So here you have y in up to y out. And these just both involve x. Maybe. Doesn't have to, but it could involve x. Also involves x. And then finally, you find what the actual overarching region of x is. X in to x out. But they're just numbers. These are just numbers. I didn't really use that. So. Okay, so that's the method. But only if you do the integral in that order. If you do the integral in a different order, then you have to start by projecting it onto the correct plane. So here, I used the xy plane because z was the first, but if x was the first, I would have had to project the shadow onto the yz plane. Okay, any questions about that so far?
When we don't have x, the shadow, how do you find the shadow?
Only the shadow knows. I don't really know exactly how to find the shadow. Basically, to find the shadow, you sort of have to just draw it and look at the geometry of the thing. And normally, you can just see it. But one way to do it is to work out all the possible values of x and y for different values of z. So you could try z equals 0 and see what you get. You could just... there's no hard and fast rule. It's very dependent on the shape. So I wish I could be more precise. But if you do a lot of examples, you'll see it's normally quite straightforward to see what the shadow is. So here's an example from a quiz, again, 2005. It says, let W be the part of the first octant below 3x plus 2y plus z equals 6. And what you have to do is set up the limit of integration in this order. So you want to convert that into a triple integral. Okay, well, let's draw a picture of it and see if we can work out what the shadow is. Here's z, here's y, here's x. Okay, so this is a plane. We know this is the equation of the plane. The normal would be 3, 2, 1, but we don't need the normal. What we really want, first of all, understand that the first octant is this corner. It's 1/8 of the space, hence octant. It's x greater than 0, y greater than 0, z greater than 0. So we don't need anything else. Now, what's the x-intercept? Well, set y and z be 0 to be 0, and x equals 2. How about the y-intercept? 2y equals 6. Y is 3. And the z-intercept? Set x and y be 0 to be 0, so z is 6. So there it is. The region is some sort of pyramid. So what's the shadow on which, well, first of all, what's the plane we need to do the shadow on? It's not involving x, it's the yz plane. So I cover up the first one and see. It's the yz plane. So I need the shadow. Now, it's quite clear that this just gets bigger and bigger, and the base of this thing is the shadow. So it's that triangle. That's the shadow. But you see, I just had to look at it to see in this particular case. Okay, so I picked some point yz in the shadow. So I fixed y and z. What I want to know is, okay, it's a bit hard, but if I start at x equals 0 and go forward out of the board, when do I bust out of this pyramid? How far do I have to go? It's really hard to draw. It's got to be parallel. So here's a point on this axis. As in, what could x possibly be? Well, then it lies on the plane. So x starts at 0. X equals 0. Here, x is on the plane. So you just solve this equation for x, and you will find, dividing by 3, that it is 2 minus 2/3 y minus z over 3. So the x region, this integral, I need plenty of space. The x goes from 0 up to 2 minus 2/3 y minus z over 3. Okay? Do you see how I worked that out? It's sort of hard geometrically. Sorry? Do it again. Okay. Maybe I'll rotate the thing. So suppose I rotate it like this. So here's the y-axis. Here's the x-axis. And here's the z-axis. Okay, so I'm starting at a point there, and I'm working up inside the thing parallel to the x-axis. So I'm actually inside my triangle here, and I'm working until I get up to the face. And so I'm parallel to this x-axis. And I start at the point here, which is 0, y, comma, z. And I finish at the point with the same y and z coordinates, and I ask you, what's the x coordinate there? And that's the coordinate of the point on the plane with those y and z coordinates. And so by solving that equation, it turned out to be 2 minus 2/3 y minus z over 3. Does that help a little bit? Okay. Again, it's all about how you draw it. Now, the next thing is we're integrating with respect to y. So I have to forget about the x now. I have to take this point yz in the plane, and I have to draw a line parallel to y to work out parallel to z. So I've now covered up, the first was to cover up the dx, now I cover up the dx and the dy. I've left with the z. So I now just take a line in this plane.
When you did the dy, we just did the x.
We did the dx. Yep.
So why not go to the dy now?
I'm going to the dy. But I'm saying, to do the dx, I needed the shadow in the yz. So I sort of covered up the dx to see that that was the case. Now I'm covering up the dy just as an aid to see which line to use. Another way of thinking about it is I need to see what are the y values that are going to work. So I don't know what I'm talking about. Forget everything I just said. Forget shadows, forget that. Look, I need to know, given this point z, what are the y values? So I do need to be perpendicular, parallel to the y. Forget what I just said. It sounded cute, but it was just silly. Okay, how do I know that I'm correct? Because I need to fix z and let y vary. So y is the variable, because I'm doing a dy, and I need to see where I'm going here. The lowest y is 0. What is the highest y? Well, what is the equation of this line here? I need to set x equals 0, so the equation of this line is 2y plus z equals 6. So that means that the highest value of y occurs on this line, and it is 6 minus z over 2. So it's 3 minus z over 2. So for the fixed z, y is going to go from 0 up till it lies on that line, which is 3 minus z over 2. Finally, z goes from 0 to 6. And that's it. All right, question?
Now, would it work when you analyze the shape from that point that you chose, right?
Yeah.
Would it work? It would work just fine if you chose another point, like say on the xy plane, right?
So the question is, I analyze it in terms of my point y comma z, and your question is, well, what if I started with a point x comma y?
Yeah, it just.
Okay, that would work, but the integral would be in a different order. It would have to be dz, dx, dy.
Yeah.
Okay, so in order to change this integral into one of the other things, you would have to identify this region, or know what the region was, and then do it from one of the other perspectives. But the question said to do it in that order, dx, dy, dz. So I had to do it like this. Okay? Any other questions about that example? Okay, should we do another one?
Why did you fix x? I mean, you told us the rule before that the first integral, that the right integral is dependent on both other variables, and then, but x changes as well.
Yeah, okay, so the question is, why did I fix x? I mean, the deal here is the first integral is with respect to dx, right? So I need, in all generality, if I start at any point here, y comma z, where's the range of x that I have to go from? So I'm going to go from 0 up to whatever that value of x is. So that covers my base no matter what my y and z is. Okay, now I have to somehow cover every possibility of y and z. So that has to now vary over here. So what I'm going to do is fix a z first, in this case, and say, well, what are the values of y? And then I'm going to let z vary. So basically it goes like this. Pick a z between 0 and 6.
Okay. You didn't really. Okay.
Okay, there's my z. Now, pick a y between 0 and 3 minus z over 2. There's my y. Now, integrate from 0 up to the correct value of x. So I now have added all those up. Repeat that for every one of these y's. Add those lengths up. So I'll get that, right? Or at least the values of f on there, because the f doesn't have to be 1. Now repeat this for every slice, and add them all up. So the first integral finds the integral of f along any one of these lines. The second step gives you the integral along any slice. And the third step adds up all the slices. And of course, you can slice it this way, I mean, depending on how you slice it. And how you slice the slice. Even if you slice it this way, which means that you're doing the dz integral last, then you can choose to slice it this way, which would mean that you do the dy integral second and the dx integral first. Or you could have done it this way. But that would just switch the dx and the dy. Okay, does that make sense? So that's why this all works. So it's saying to add up a volume, or a function f over space, you just add it up along lots of lines, then you add up all the lines to get the thing over a plane, or a planar region, then you stack them to get the volume. Kind of neat, kind of neat. Fubini thought of this. He was the man. Now, here's another question. There's 2 more questions. Let's do this one. It's a quiz from fall 2005. Triple integral. 0 to 1, x to 1, 0 to 1 minus y squared. E to the z over z minus 1. dz dy dx. Okay, so the question could just have been, find this. But you see, in order to find this as it stands, you would have to be able to integrate e to the z over z minus 1, because the first integral that you have is like this, just a dz integral. But that's a really hard integral. It's probably impossible. So the question actually says, sketch the region of integration, and also, by changing the order of integration, solve the problem. So, yeah. So we have 6 to do. So we're going to draw the thing. So here's how I'm going to draw it. There's z, y, x. Okay, according to this, for a fixed point in the y and x plane, so x is going to go from 0 to 1. That's the first thing I know. So for a fixed point in the x and y plane, z has to go up to 1 minus y squared. So I'm going to graph. So I have this. That I know. So let's graph this. Z equals 1 minus y squared. So that is a parabola in the zy plane. Intercept 1 and minus 1 to 1. Okay, so that's the restriction on z regardless of what x is. So actually, if I just draw this curve, z equals 1 minus y squared, it's a cylinder. And, you know, you could imagine it keep going, but you don't actually need to because x only goes from 0 to 1. And then the bottom of the thing is just z equals 0, which is the xy plane. So if it weren't for this x here, if we didn't know what y did, can you imagine this becomes a tent? It's basically a tent. Okay, but we do have to deal with the x here. See, we also know that y is bigger than x, but less than 1. So that means here's the line y equals x. And so if you don't know, you need the part where y is bigger than it up to 1. So it has this base. Here's the base of the region. So it's the intersection of this tent with this everything inside that line. So if I have to draw it again, it looks like this. I only need this part. Yeah, it's only part of the tent. In fact, it's sort of this part of the tent. It's like a wedge. That's what it's going to look like. Okay, so I'm just taking a cleaver to this tent and only chopping off a little corner of it. It's got a little wedge shape of the tent. So the boundary of this is the line y equals 1. So this is y equals 1. This is y equals x. And this is z equals y squared minus 1 minus y squared. Okay? Is that all clear? Now, we have to change the order of integration. So, I propose to do the x1 first, because that's what I did when I tried to work the problem. I know I don't want to do z first, and I have no idea whether to do y first or x first. I just tried x and it happened to work. You can try y and see if that works too. But I said, okay, what the hey, I'll try x first. Let me redraw this over here just really quickly. Parabola, y equals x, y equals 1. And that's what that section will look like. And everything is 1. Okay, so I said I want to set this integral up. So the integral I want, which I'm going to call I, capital I, I've got to integrate still e to the z over z minus 1. But let's do it dx first, and then dy, and then dz. Okay, the basic idea is I can't do the z integral, so I kind of want to put it off as long as possible. Okay, so in this case, I need the shadow on the yz plane, because I'm going to do x first. So the shadow is this back piece here. This is the shadow. And that's, again, z equals 1 minus y squared. Okay, so how does that help? Well, where does x go from? If you start inside that shadow and come out until you hit this surface here, where's x going to go from? Well, it starts at 0, and it just goes until it hits this corner here, which means it goes up to y. Another way of doing it, by the way, and not a bad way at all, is to rewrite those three inequalities. 0 is less than or equal to z is less than or equal to 1 minus y squared, and x is less than y is less than 1, because the y integral in the original went from x to 1. But you can just look at this and say, oh, well, x is going to go up to y. So this actually means that if you're just concerned about x, it has to be less than y, and of course in the picture you can see it has to be greater than 0. So what I'm saying is either geometrically, whatever the value of y is here, that's where x is going to go up to. The z value is irrelevant, and I claim that the x piece goes from 0 to y. I doubt they're doing triple integrals. All right. It's probably a math joke. All right. Now, okay, so we've gone from 0 up to y. Now, the next thing we have to do is say, okay, we want to know where y goes given a value of z. So we know where z goes given a value of y. We need to invert this inequality and see that y goes up to root 1 minus z. I just made y the subject here, y squared less than or equal to, and take the square root to get the 1 minus z. And of course y is going to start from 0. So it's going to go from 0 up to that value of y, which is root 1 minus z. And finally, the z range goes from 0 to 1. Okay, so, okay, question.
Why are the poles of integration in terms of x from 0 to y? Doesn't it kind of curve closer to the x-axis?
So the question is, wouldn't it depend on what the z is? No, this face, although it has a curvy top, is just cleaved down along the line y equals x. It's flat. It's a flat face. So actually the z value doesn't matter. And you can see it from here as well. If I just tell you what y and z are, where can x be? How big could x possibly be? Well, x doesn't care about z, but it has to be less than or equal to y. I'll just re-establish where I got these from. Over here. Z goes between 0 and 1 minus y squared. Y goes between x and 1. So if you're flipping this around and you want to know what happens to x, clearly the highest it can be is y, but it doesn't care what z is. Okay, and you can see it geometrically if you think of this face as just flat. It doesn't matter how high up you are. It's the same region. I agree that if you're closer there, it's smaller. But then see, y will be small. If y is only, say, a quarter, then the x will only be a quarter.
Once you set up the first, I guess the innermost interval,
Yep.
you only use that shadow to set up the
That's right. Exactly. You use the shadow to set up the second interval, which is the y in this case. Okay, so now we can do this. The first integral, in terms of dx, the function doesn't depend on dx. So this will look like this. You just get the length of this. The integral dx is just x, so y minus 0. So it's y. Okay, now we need to, this is a constant again. so it's not going to matter. It's a constant with respect to y. So we just have the integral of y. The integral of y, so I'll leave the e to the z over z minus 1. The integral of y dy is y squared over 2 plus c. So using that, I have y squared over 2 evaluated between 0 and root 1 minus z. Well, the 0 part doesn't contribute. So this integral is the integral from 0 to 1, e to the z over z minus 1, times plug in root 1 minus z, and magically it is 1 minus z. But then you have a 2 dz. And now this cancels out and leaves a minus 1. So this is just the integral of minus e to the z dz, which is minus e to the z between 0 and 1, which works out to be 1 minus e. So it works. Oh, the 2 disappeared. Thank you. It was right there. 1 minus e, all over 2. Thank you. Okay, so difficult practice. Any questions about that? Okay, you have a question for me.
It's fine, this is going to help you.
This is help enough? All right. I could do one more, but probably not in 3 minutes. Shall we just leave it? Any other questions? All right, next week. Wait, I do have one more thing to say that I can tell you in 3 minutes. I'm sorry. I can tell you in 1 minute. Probably 2. And I'll fit it on this board. I forgot to tell you a very simple formula. The volume of the region, or of a W, some surface, is just this. 1 dV. Okay? So if you can do a triple integral, then, you know, the ones we've done had functions in them, like e to the z over z minus 1, or f was not even known. But if the function is 1, it just gives you the volume of the region. So if you're asked to find the volume of a region, you use a triple integral with an integrand of 1. Okay, so that's one thing I have to tell you. You just have to learn that, or at least understand why it's true, and then be prepared to find a volume using a triple integral.
That volume is the same volume that we would have gotten with a double integral and a function.
Okay, that could be the same as a double integral and a function, but if you had the function, then the z part of the integral would be from 0 to that function. Okay, the thing I'm trying to tell you in my 1 minute left is that the average value of a function f over w, again, this generalizes the two-dimensional version, is 1 over the volume of w times the triple integral over w of f dv. So you're expected to know that. And again, as in the two-dimensional case, the practical point of this is that you set it up as a ratio of 2 triple integrals. One has the function you're concerned about, but the other, being the volume, just has a 1. And the beauty of this is, as you've seen, most of the effort is expending in actually setting up the thing. The integration is not so bad. So you have the same setup in both because it's the same region. In one case you use the f, and in the other case you use the 1. So if you ever have to compute an average value, that's the formula. I put it in parentheses because this is the real formula, but this is the practical computational one. So it doesn't really add anything to what I said in terms of techniques, but they are formulas you need to know. And next week, the first example will be an average value or a volume or something like that, okay?